Whenever we have a snappy day in the Bay Area, I'm reminded of one of my favorite 30 Rock lines. It's a total throwaway line when Liz Lemon's rival is going to move out to the Bay Area. And she, in a way of disparaging the Bay Area, says, well, enjoy carrying a light sweater around for the rest of your life. And which I definitely feel is like the Bay Area living for sure.
It's a good burn.
It's a good sick Bay Area burn. Anyway, Jordan, it's great to have you here. In preparation for this, we did an episode on time, not on high resolution time. This is different. But I started getting this budding paranoia that I would repeat some of the same anecdotes. Is there a name for this phobia? Or it's just fear of dementia, Adam? Is there a specific name for this? I don't know what it is.
Oh, no, but I think that you and I suffer from it acutely. In part also because like we both have wives who are like, nope, heard it. Like
I've definitely heard this one before.
Turn
Exactly.
the page, right?
Oh, I know. So I went back and just to make sure I had my anecdotal bases covered, I listened to our time episode at 3x, which was an interesting kind of experience. I kind of felt like, when you got like the cat with the laser pointer, and Jordan, you're a new owner of the cat, so I'm sure you'll appreciate this. You get like the cat with the laser pointer and you kind of like are dragging the laser pointer around and you're amusing yourself. And finally you get sick of it and you just start scribbling the laser pointer on the wall and just watch them just lose their minds. That's kind of how I felt like listening to us at 3x. But then it was actually listening to us at 2x felt very intelligible. So
good. Well, I think it's a good announcement. This can be 0% post-consumer product or whatever. All new anecdotes.
This is all new anecdotes, all the fresh stuff. And part of the reason I was concerned about that is because this is also kind of going back into my own way back dial in terms, because this is one of the first things I worked on as a young engineer was time, and in particular using high resolution time as a basis for timekeeping and all of the problems with that. So, and Jordan, what if we maybe wanted to start there in terms of maybe you could describe what TSC is, the timestamp counter is, and kind of what it's used for in the operating system, and then maybe we can get from there into some of the challenges we had in terms of virtualizing it.
Yeah, sure. TSC, as you called it, is the timestamp counter on x86. I think of it as just kind of the basis for monotonic time in the system. So anytime you want to measure a duration or an interval, you would use probably something that is based on the TSC. It is also an MSR, which means that it's writable as well, which adds some additional wrinkles to thinking about virtualizing and migration VMs. Like the simplest example is HR time, high res time, which is like nanoseconds since boot, but that's computed from the TSC in terms of the number of ticks, which is usually thought of as like clock cycles, and then a frequency.
Right. So let's expand on that a bit, because you've got the frequency at which TSC is moving is, and this has changed with various parts over the years, but it is more or less a base CPU frequency. And
that's right.
Back in the day, one of the things we discovered, at least when I first did this tick-based time work on UltraSpark, is it turns out these parts were actually not 167 megahertz, that they were actually 166.996 megahertz, and that or they would vary, and that difference could be really meaningful, and you would lose the ability to keep time if you didn't. You need to know the frequency with which this thing is, because you want to turn it into something that is like meaningful to humans, ultimately like fractions of a second, nanoseconds. But the frequency on x86, because x86 has had variable frequency for so long, you've got a defined base frequency for TSC. Is that right?
Yeah, I mean, in terms of the promises made by the architecture, I'm less familiar with that, but I do know that it's not exactly necessarily the CPU frequency. So like one of the things that Illumos does on boot is calibrate the frequency of the TSC and measuring it against a different time source, the PIT, I think. And we use that as the frequency for the system forever, because there's certainly things that can introduce jitter into that, but it seems to be good enough these days.
Yeah, the pitting, the programmable interrupt timer is the 8254, which of course hasn't existed as a discrete part forever. It's just effectively an emulated part. But all right, so we've got the challenge, and you mentioned that it's an MSR. Do you want to elaborate a little bit on what an MSR is and what that means for the architecture?
Yeah, I mean, my understanding of it, I think it's model specific is what MS, and then R is register. So it's a register programmed by, I guess, the operating system. Like it's something that is in certainly a higher privilege context. But the TSC actually is writable, I believe, from, actually, I don't know off the top of my head. But yeah, importantly, the guest can write to it, whether that's
Right.
space or the kernel.
Right.
But,
The guest operating system. All right. So what is the challenge in terms of virtualizing this thing? Because we've got we are developing our own hypervisor, Propolis, which is beehive based, and we need to tell the lie of the TSC, which we've got some hardware support from, certainly. But so what's involved in virtualizing it, and then as kind of an entree into the thorny problem that you found.
Yeah. So I think it's good to review kind of what the expectations are of system and its TSC. So I mentioned like think of HR time as nanoseconds since boot. So the expectation is that the TSC starts at 0 on boot, which is not actually always true due to errata, but at least following processor reset. So it starts at 0 and then it increments forever unless it's written to or the processor is reset. So from a guest operating system perspective, that's what you would expect, right? Like from the time that the guest is booted and having no real knowledge that it's on virtual hardware, its THC should behave that way. Then kind of another thing that may not be super obvious in that paradigm is the guest frequency also should not change. So when we're talking about live migration, we're moving guests between machines. As I mentioned earlier, the TSC is calibrated on boot, at least on Illumos. I think that's true of other systems as well. So even if two machines have the same CPU, they will not necessarily have the exact same CPU frequency. If they're the same, hardware, they're probably going to be pretty similar, but they're not going to be precisely the same. And so that is another challenge of moving between machines. I can get into like the details of how it's virtualized next.
I mean, it's like I think that one of the things that is frustrating about this problem is that in order to be good enough, it really has to be quite good. That you need in order for NTP to be able to rely on it, you need to actually. I mean, you need to be within 64 parts per million, which is like very sloppy from a time perspective, but it's pretty. I mean, the approximations are often not good enough. You actually really. It's a tough problem in that regard that you can have these things that are putatively the same frequency, but their minor differences in frequency are in fact enough to introduce error into guest. So it's a problem.
Yeah. So in terms of virtualizing it, there's sort of two different jobs in the hardware provided by both Intel VMX and AMD SVM for virtualizing the TSC. And by hardware, I mean when you read the TSC from the guest perspective, generally you will not take a VM exit into the hypervisor. And the first one is the TSC offset. So you imagine like a simple case of just like a guest running on a machine, no migration, same frequency between the guest and the host. When you think about what the guest TSC should be, you can simply take the TSC of when on the host of when the guest was booted. So if it's booted like, I don't know, 2 days into the host's lifetime, TSC for the host, then you can negate that and add that to the host TSC to get the guest TSC. So at the time that it boots, that value plus negative itself is 0, and then it'll increment along with the host TSC. So that the component of adding something to the host TSC is the TSC offset. So that's the first thing that we can virtualize. And until I had started working on this problem for live migration, that's how beehive things today. Was simply storing that TSC, negating it, and adding that to the VMCS when guest is run.
So, and just to define things for folks a little bit, so the VMCS, do you want to just describe that a little bit? Because and maybe you also want to describe what a VM exit is, what a guest exit is, and why we want to avoid them.
Yeah, so pretty like basic operation of a guest is, I'm going to talk about AMD because that's what I've been looking at more lately, but as like the VM run instruction. And in that instruction, you provide a page of data that has a bunch of stuff related to running the guest. So, all his processor state, and then these things called control bits. And the TSC offset is one of those. And so that way, when the hardware enters guest context, it has all the state it needs to kind of construct the guest view of the world. I forgot what your other question
and
was.
I'm just always kind of blown away by how much silicon support there is for this. So whenever you are running any instance that you have anywhere in the cloud, you are in one of these hardware contexts that system software has programmed and prepared, and then the hardware is doing this. And so the work of minimizing these guest exits, where a guest can't do something, so it's like I don't know how to do this, and the hardware doesn't support this, so I need to kick out of this into the operating system. And we want to avoid those. We want to allow the guest to operate inside this hardware virtualized context as much as possible. So sorry.
And read TSC is an instruction in x86, and that one is generally not emulated, so we don't get the exit in that case. And if you think about how often that instruction is called, it would be like
devastating.
Completely
Yeah,
it would be very
bad. Yeah. But so we historically, kind of prior to you doing this work, what beehive had done is a reasonable thing to do is I've got the offset, I'm going to program that in the VMCS, and off the guest goes.
That's right.
But that's not good enough for us.
Yeah, so that's not good enough for migration. So this is kind of this area of the problem is where I started to get into the other thing you wanted to talk about, I think, which was the little simulator program I wrote. So yeah, we're working kind of out the math here from first principles was something I found a little difficult, in part because I don't think anyone has sat down and written formulas down that I needed before until I did for this process. So if you imagine just like taking a guest and its TSC offset and moving it to another machine, that doesn't make any sense on the context of a different machine because the TSC is a monotonic counter. It only makes sense in the context of a single environment. Additionally, like the way that we are virtualizing this is through a relative time, right, to the guest booting on a host, and that relationship also has no bearing on a different system. So you definitely need some more information kind of in this to start to figure out how to virtualize that in a new environment.
So what was some of the new information that we in terms of like what is the actual math of having to move this thing?
Yeah, so the way I think of it is like a new, I call it effective boot time in my head. But basically, like we have this relative point in time or where the guest TSC is relative to the host. We move to a new host, we need to find that new relative point in time. The one thing you can take is the new host's current TSC for when the guest, say, is now running on this new host. But you also need to know how long guest has been running, right? Because as I mentioned, like the new host that TSC has no conception that the new host and its TSC is not sufficient to describe how long the guest has been running. So what kind of the interface I ended up landing on is taking a snapshot of host A's TSC, or actually I use HR time, a representation of the TSC and the guest TSC, because that is fully calculable. And then we ship that over to the target host, and then using those two pieces of data can reconstruct a new offset. It's not as simple as just doing that because there's also frequency differences involved. Does that make sense so far?
Yeah, so far. And I was actually going to drop in a link to. Would it make it sense to drop in a link to your the commit, the Illumos commit? That's got a lot of block comments that can help had to
Yeah.
orient folks. I'm not sure if drop that into the chat, but
Yeah, it's hard to talk about this because there is a lot of math, but having some formulas in front of you is helpful.
so yeah, so you kind of bundle this up, and you want to describe actually just the live migration problem a little bit and why that's important.
Yeah, well, for time specifically, or
Just in general. I mean, like why would we migrate a VM? That sounds like a giant pain in the ass.
That it is. But it has a lot of benefits, right? From someone like Oxide's perspective, which is running a set of infrastructure, it is very useful to be able to do things like update, servers or, host operating system software, whatever it is, without inflicting downtime on customer instances. So live migration is a useful tool to have for all sorts of things in terms of managing infrastructure. In terms of like the mechanics of how it works, it's like both very simple and very complicated, I think. It's sort of helpful, I think, to kind of decompose what a guest is into different pieces. So we have like its CPUs, vCPUs. We have a bunch of emulated devices, which is done by both Propolis and beehive. And then there's some kind of other nebulous things like CPU state, or like in the case of the TSC, this is sort of like a weird one that it doesn't really cleanly map to devices or CPU. And then we also have memory. And so the live migration process itself kind of finds a way to pause all of those different things, take a snapshot of some set of state that is useful to reconstruct on the other side. So very simple, but also, there's a lot of details in there that can get very gnarly, such as the TSC.
And Jordan, what are some of the constraints on migration? I mean, presumably we want the guest not really to notice that this happened. What are some areas in which the guest can be sensitive to noticing that this happened and freaking out?
I mean, just time, like jumping forward is one of them for sure. So if you were to imagine not doing anything with the TSC, or rather the state that we stored previous to this work, it kind of like in state of what time the VM thinks it's in is completely unknown, and that can cause all sorts of problems.
I mean, it's bad when time jumps forward, and it's very, very, very bad when time jumps backwards. Like that monotonically increasing time really can't go backwards.
Yeah, and to be clear, like time does jump forward a little bit because in this work we do account for the passing of time and migration, which I can also talk about. But yeah, like that would be very bad. Obviously, you don't want to have state situation where state is modified on the source after it's already been sent to the target. So that's why there's like a pause step in all of these different components, whether it's memory or CPU or devices, so that you can have a clean state of the world. But yeah, beyond that, at some point you have to stop the world, send everything over, and start again.
Yeah, and it's so important to have this. I mean, and Adam, you did not having this is just brutal when you can't move things, because it just snowballs, right? Like you can't ever take something down for maintenance, obviously, because you can't, no one, there's no such thing as arranging downtime for people. You know what I mean?
Yeah.
But everyone's like, well, actually, my thing is way too important. We can't take it down. And then you end up with these kind of, when people look at kind of utilization across a data center and see very low utilization, this is part of the reason for it, because you end up with these islands that are kind of unprovisionable, that have a small number of resources that can't be deprovisioned because that there is no capacity to be, assuming you don't have vMotion or you don't have another technology that allows you to live migrate. It just snowballs. It's such a mess. So that's as difficult a problem as live migration is. We viewed it as a real constraint on the problem, not wanting to, in the spirit of fighting the last war, we just did not want to have all the problems we had to join. So Jordan, you are yes, TSC is one of these kind of oddballs that you've got to go deal with, and if you don't deal with it, the guest will be upset with you.
Right, and I definitely saw that in my kind of initial. One thing that I observed about working on this project just like as a meta observation, was that I did a lot of prototyping because I found the problem space very complicated and confusing and mathy, and it was helpful to just sort of build out small pieces at a time. So I started with, migrating, since we already had most of this migration work already done, just migrating a guest and seeing what happened. And sometimes things would work fine. Sometimes it would just go off into space and never come back, or I would see errors from like get time of day.
And so this was when
So
you were
yeah,
walking up to the problem. Like, so you haven't I have not solved this problem here. I just want to get a flavor for what happens if we don't solve this.
yeah, that's right. And like I didn't expect it to work, but it was interesting how often it did just happen to work. And maybe that's because the uptime of the two hosts were similar and just kind of some implementation details and the way we were virtualizing it today.
Interesting.
But definitely things could go very wrong and be very difficult to debug.
And then then you mentioned like doing little prototypes. Do you want to elaborate on those? Because maybe I can drop in a link here because I did love this little simulator you wrote.
Yeah, that one was like maybe kind of after some exploration a bit. So I still haven't talked about frequency, how we handle frequency.
Yeah. Go into that first.
Well, so like the reason I mention it was that I kind of started the problem by only thinking about how to correct the offset. As I mentioned, you can compute a new one, assuming frequency is identical, using kind of the snapshot of state from when the guest is migrated, what its TSC is and what the host TSC is. But then you add in frequency and things get kind of weird. And so I was trying to kind of work out for myself what the math there of how you construct this state in a correct way. So I ended up writing, a Rust program to help me kind of prove out that I had like done it correctly, basically. So the answer is like not very complicated. Basically, anytime you're adding together TSC values, you want them to be from the same frequency, right? But when you have migration on the scene, and a guest boots, we give it the frequency of the host it's running on. Makes sense for tons of reasons. But when it migrates, it might be running on a host of a different frequency. So the next kind of knob that is available in hardware virtualization is a frequency multiplier, which will it's a ratio of the guest frequency to host frequency. And the hardware, when it will read the TSC, will then multiply that value by the frequency multiplier and then add the offset.
And this is really where the white lies turn into a real conspiracy here. I guess where the hardware is really helping you. I get it. Like, let's lie to this guest. Like, I'm gonna help you. I'm gonna help you really lie to this guest. And it's like, you want to run this guest on a slower CPU? I got you. I'm gonna help you out.
Yeah, I mean, it is a straight up lie, but it's very convenient for what I needed to do. Also in the Intel manual versus the AMD manual, they both describe this process pretty differently. So this was another area where I was just staring and like doing math in my notebook. But ultimately, they both represent the multiplier with a fixed point number. So like an example of a fixed point number is like dollars and cents, where you have these 2 digits reserved after the decimal point that represent cents and have a different base. And so in binary, there's some number of bits that are reserved for the fractional component of the ratio, and then there are some amount that are for the integer component. But the way that Intel describes frequency ratio is like very strange to me.
And presumably this was all built and designed for this use case precisely.
Yeah, I mean, Yes, yeah, I assume so. The language, it talks about specifically like shifting the shifts that you do, but doesn't really motivate like why you're shifting and multiplying. That has to do.
What's the range of ratios here? I'm sort of surprised that there's like a potentially large integer component, but maybe I'm under imagining how different various CPUs could be in terms of the rate at which TSC is moving.
Yeah, that's a good question. One thing I thought about a lot and maybe like over kind of rotated on was kind of what reasonable limits were around what ratios should be allowed. practice for like, at least the focus of the work that I was doing was for Oxide, so we're using, the same hardware. But like, so this is in Illumos and should be general purpose. But I basically concluded that like, I think I forget the exact number I picked. So I think it was like 15x was the max I picked. And I basically went back and looked through a bunch of different CPUs over time to kind of
15x.
see.
What
That
a
is like,
whopper of a lie
that is the high bound.
That is a
like,
whopper. You think you're on a CPU that's 15x faster than what you're actually running on. Like, oof.
Well,
hope you're not like.
Yeah.
That's like, because if you're just like, wait a minute, like I'm looking at the passage of time versus the number of instructions that I'm executing. I mean, it just feels like you're gonna get caught out at 15x. I don't know.
It's not something I expect to happen. This was me picking a limit to return an error in the kernel.
Hey, Jordan,
like, I think.
Not to put you too much on the spot in terms of numbers, but do you have any empirical data about, as you say, in our lab, it's sort of all the same CPU migrating from the same flavor to the same flavor. But do you have a sense of like what the range of ratios you saw even among, these parts that, came in the same box?
Yeah, I actually at one point did a survey of a bunch of gimlets in a rack. And they were within 14 parts per million of each other frequency. So definitely not a big difference at all.
Really, I'm actually amazed it's that much. Yeesh. I'm amazed it's that much. I mean, that's good that 14 ppm is well within like the 64 ppm that is like the outer limit for NTP, but that's still a lot, man. That's a lot.
Yeah, and that was like one survey months ago. I basically did it as a way to quickly confirm that, it looked pretty similar.
Yeah, right.
I thought the NTP threshold was a bit bigger though, like 500 ppm.
Oh, interesting. Okay, yeah, maybe. Well, just like my fear of repeating anecdotes. I'm sure I got this wrong, but there is variance. I mean, it's minor, but it is absolutely observable, and it will be observable. The other problem about time is that it actually continues forever. So these small differences will actually add up to big differences in the future, to the point where a guest will lose track of time or will realize that it needs to make an adjustment. So it's like it is actually important that we, even those small differences, we compensate for correctly.
Yeah, so we can talk a little bit about that next if you'd like.
Sure.
Because that's a really hard problem. Kind of the solution we landed on. So specifically, I'm talking about when you migrate between machines to the point from which like the guest world stops and to the point where it starts again. There's some amount of time there. Figuring out how to compute that's pretty difficult because again, we're dealing with monotonic time, which has no relationship between machine A and machine B. So in the Oxide track, we were running NTP on all these machines. So as part of the interface snapshot, I also added a wall clock snapshot time, which is not a perfect way to measure a delta between machines because wall clock time, unlike monotonic time, can go backwards. But we assume in a pretty load-bearing way that NTP is running. So then using the wall clock time, we can determine how long migration took, or rather how long it took between these two readings of the TSC, and move the guest TSC forward accordingly. But
the guest will see, and is that transparency that you want to offer to the guest? That is just it's kind of a courtesy to the guest. Or does that end up being a correctness issue because you want the guest to make sure that if it's using this to track wall time, that it doesn't get completely confused?
Yeah, I mean, it would be a pretty weird state if real time moved forward, I don't know, 10 seconds or whatever, and the TSC didn't move at all.
Right, sure, yeah.
So that is kind of the solution we landed on, but it's very imperfect because it, again, really relies upon NTP. But I think without NTP, otherwise you end up implementing, something like NTP.
Right. So you figure out make an estimate for what our kind of blackout time is, the time that we've been under general anesthesia, and then you add that presumably to the offset on the destination, and that needs to be close to the last thing you do to actually run this thing, right?
Yeah, so this actually gets a little tricky. It's not tricky actually. This was a situation in this project where I found that my mental model of how things should work and the way the implementation should look were actually kind of different. And the result was that the implementation looked simpler. So yeah, my mental model was very much like we kind of measure this time between pausing the world and restarting the world, and then you add that difference. But it doesn't really matter, like actually when you do that measurement, if that makes sense, because the guess TSC is purely like you're able to calculate it completely. So as long as you have a snapshot on the target, or excuse me, a snapshot on the source, which is like the guess starts, and then on the target, no matter when you read or write that data, as long as you do them from one after the other, it'll work out. That is definitely my mental model for how I think about it, but doing it strictly that way introduces some weird complexity into the protocol that makes it a lot harder to reason about.
Yeah, interesting. So it actually the implementation ended up being a bit simpler then.
Yep, we just, there's like a step where we read that data, send it over, and write it back out, and it doesn't have to be at the beginning and the end or something like that. But it's not intuitive. That's like a lot of the stuff I find very unintuitive. I have to stare up for a while.
Yeah, and then so what were some of the issues that you had when you're developing this? I mean, I know that you at one point you're like, I need to go write this simulator, which I love. I feel like that's Adam. I think I know that Josh did that when we were working on the storage subsystem. I know we've just done that a bunch of times in our careers. You're just like, all right, I need to go write a simplified version of this outside of the system. Like, forget where I can go just iterate on the kind of the core principles really quickly. And Jordan, have you done that? I mean, I assume that's a technique that have you used that technique before, and kind of what was it valuable here?
Yeah, I use that technique a lot in terms of like implementing a small piece of something to kind of verify it works on its own. I'll write a lot of like I have a a directory on my dev machine called play that's just like filled with small C programs or Rust programs or whatever,
Nice.
trying stuff out. This is definitely a little bit more involved than what I normally do, but it proved to be really useful in part. I mean, for a bunch of reasons. One of them was that the some of the math here uh, ended up needing to be done in assembly because it had to live in the kernel, so it wasn't going to be in Rust. And also because some of the intermediate representations are in 128 bits, which you can do with Rust, not the kernel. And so I wrote this simulator first and had all this like math written in Rust and kind of had cases to handle overflow and help me like test out the edges, sort of where those like different ratio limits should be. But then when it came time to actually write assembly code, I was able to just kind of plug it in to this Rust program and test that independently before I even tried, using it in my kernel change, which was really cool. And I ended up writing a bunch of tests to run against it in that little simulator as well, which was mostly just for my own sanity. But yeah, it was definitely valuable for many reasons.
Yeah, that's really cool. And then you've got something that is small in front of you that you can reason about. So when you do have an issue, you can really understand. Like, I mean, so when you're doing 128 bits, you're going from 64-bit to 128-bit to do this math. And I mean, there are edge conditions that you need to deal with there, right? I'm sure it was much easier to deal with that at user level and kind of a user level program.
Yeah, and also like, again, starting like very prototype heavy, like doing Rust first helped me really think about like where all these edge cases are. And then when it came time to kind of do it in a more unsafe environment, I felt like I had a good understanding of where things could trip.
It's really cool. I don't know how many times. Yeah, I mean, it's kind of funny that we're using Rust to prototype aspects of the system that have to be done in assembly or in C. But that's where we are. I mean, it definitely makes sense how we got here, but that's really neat. So and did you end up finding bugs in the simulator that proved to be useful?
Oh, definitely when I was writing the assembly. um, the math itself isn't like that complicated, so I don't think I found any bugs necessarily with that. But when I was testing changes on like real machines. It was really, really nice to be able to walk up to the system and grab things off of the struct VM and MDB and then pass it into this calculator I'd written. Like another thing, I was reviewing the code for the simulator before this, and I remembered that I added Clap has a feature that lets you, it's like called maybe hex. So you can pass in like either decimal or hex, which was so useful because I tend to like think in decimal more, but then when I was getting stuff from MDB, it was always in hex. It was very nice to be able to throw both in there.
Clap add this. I've been using parse int for this. I've not.
Oh.
So Clap's kind of built in for this.
Yeah, that's how I discovered it.
Ah,
I got really tired of
Parse
deciding
int.
which one I wanted.
What's this clap num maybe hex? How long have you
Pretty
existed?
fancy.
You
Oh,
Yeah.
sorry.
little
I guess it's from
rascal.
clap num. Yeah, not clap, but still.
That's and had you used clap before? Clap is really. I know people got. I really like clap. I'm
I
just
like
saying that. I like clap.
Yeah.
Adam.
I'm really into Clap. Also, Clap makes use of auto ref specialization, which is one of my favorite like crazy macro-y Rust hacks.
Go on. What's auto ref
So have you
specialization?
ever seen like an error from Clap that's like, I don't know how to convert this thing to a string. I tried ref the thing, I tried double ref the thing, I tried triple ref the thing, I tried quadruple ref the thing, and like, geez, like Clap, give up already. Like that's not right. Auto ref specialization is a way of sort of narrowly implementing specialization. That is to say, kind of override, like deciding which trait impl to choose. And you can do this based on sort of prefixing a number of, ampersands. And then it'll try it, the compiler will, if you have like ampersand, 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 it'll try it with one fewer and then two fewer and so forth. So it's a way of narrowly kind of choosing whether in clap, for example, it uses from stir or it uses one of its built-in, wacky kind of format, string parser things.
Huh. Yeah, I did not
Yeah.
realize that at all. And clap is just, it just makes it super easy to churn out these like programs that have kind of reasonable behavior that I really, and I mean, with only some things that drive me nuts.
It's great, and I'm with you. I mean, it's Jordan. Not surprising at all that you turned to it here, because I mean, I would much rather, I'd rather use Rust and Clap than like anything else for like a tool that I run more than 3 times, I guess.
The other thing I will say about Clap that I really like is that they've been really good about pulling in things that obviously work. Because it used to be that struct opt was this kind of separate crate, and Jordan, what you're using here as Clap directives were actually struct opt directives. And I thought it was good that Clap's like, you know what, that's useful functionality. We need to pull that in. And it's good. I mean, I think it's Clap. If you're listening, I'd like to be able to use the -h option for something that's not help. There, I've said it. Okay, there we are. I'm done.
I actually found like a new clap feature just today. It's like defer, basically, rather than having to populate all of these commands a priori, it gives you an opportunity to only populate subcommands or whatever when someone has invoked that subcommand. I just feel like they're always adding new
Oh, I would go to ClapCon.
Yeah, for sure.
No, I just feel like I feel like the hallway track of ClapCon, I would learn a lot. I feel like there's like this, like maybe Hex. I feel there are a lot of like little doodads. Like I use argument groups a lot.
On maybe
Command
Hex,
groups.
yeah.
I don't know if you use
command groups are great. Yeah.
Where you say like, these kind of commands are all in the same group, and then you need to have one of these, or you can have multiples of these. I love the ability to specify that that you can have a single value here, you can have multiple values. This can take multiple values, and you can set the delimiter. I mean, it's really, I like the bells and whistles. It's fancy, and I like it. And Jordan, had you done clap based stuff before, or is this
Yeah, I've used it before. I definitely like stretched, the features a bit that I used a bit more on this. I had like one of the things I really wanted to be able to do was pass in a single command line, like a specification for a guest moving between multiple machines. So like start with like this guest frequency and this, initial TSC, and then this host has this frequency and this TSC, and then at time T, like migrate to this one. And so that proved to be a bit more difficult, but I landed on something I was happy with.
That's very cool. And then you've been able, and then if you do see a problem kind of in the wild, you were mentioning pulling this kind of actual data from an actual machine with the debugger, with MDB, and then being able to feed that into your simulator and know exactly what it's actually going to go do.
Yeah, I think I did find at least one, or I debugged at least one thing with it, which if I remember correctly, I did not actually set the frequency multiplier on the system, and that resulted in some pretty confusing behavior.
Does
But
that mean
yeah, it was.
it just like had whatever garbage was there? So it was like running at some random multiple?
I think it was a reset value is 1, so I think it was
Oh, okay.
that was fine. But the data I was seeing like on the structure didn't make any sense.
Interesting.
Yeah, and it was very useful. At some point I thought about like actually kind of writing something to pull stuff from MDB automatically and dump it in there, and I never quite needed that. But it's definitely doable, with a command line tool.
That's very great. So you're able to get confident. You're able to get confidence in the assembly. You know the assembly for this thing works. And then what were some of the latent kind of TSC problems once you had kind of the math figured out and the simulator figured out? What was involved in getting it kind of all the way integrated?
Yeah, I mean, it pretty much worked. The interface and, like I said, math are not that complicated once you kind of work them all out. But it was helpful for verifying that the data I was seeing was correct and kind of ad hoc experiments. I did a lot of a test I ran all the time was like running read TSC. I wrote like a program to call read TSC directly and just running that binary in a loop every second. And then looking at the output on the console, migrating the guest, and then seeing where it picked up and making sure that those deltas looked about right, because it's not going to match precisely, but like it should be about a couple seconds or whatever, and that they continue to increment at that same frequency. That was fun. I did a lot of that and a lot of like doing that back and forth between multiple machines, and that was very useful for those quick calculations.
And then we will be able so right now our multiple sleds vary by frequency only by a couple parts per million, but we know that in the future when we have, for example, general based sleds, you might be able to take there may be a much more significant delta in frequency, and we'll be able to effectively accommodate that with all this.
Yeah, because it's all in the hardware. There's also like anything that is hardware virtualized, I think, can basically also be software virtualized, and that like it's possible to kind of turn off this feature for read TSC, say. So we do emulate read TSC instruction, or because it's an MSR, also read MSR of the TSC MSR. And so all of that also does all of this math too, which is why it ended up needing to be in the kernel, since most of this is done on the hardware.
Yeah, and then could you speak to a little bit of the beehive testing? Because I mean, a lot of this was just the actual testing apparatus in beehive to test this. Do you want to talk about that a little bit?
Yeah, I think that's really cool. I demoed this internally. It was not something I wrote, but I used it a lot for testing. Basically, like in our beehive test framework, we have the ability to kind of spin up a guest, and it's a super simple guest with just like we just take the text of it and just smash a little test program in there. So it's like literally, maybe 100 instructions or something, depending what it is at most. And so
God's own unikernel.
wow. So
Sorry.
it's all right. So I wrote some tests that will like, do pretty basic stuff. Like one that I thought was kind of fun was the one testing frequency control. So basically like changing the frequency through a, so I guess let me back up. Structure of this test is there's like a guest file of like assembly or C that's doing what the guest is doing. So it's probably reading some instruction or whatever, and then there's an actual test that has simple interfaces to call into that. So through I/O ports, the test can send data to the guest or read data from the guest. And so frequency control test would basically read the TSC and then wait some number of ticks on the test side. And so every in seconds, the test would see what the guest thought its TSC was, which is actually running in real guest context, and then do some calculations to see whether that's within an acceptable range. So we could do things like, even though the system has whatever frequency it has, we can change the guest frequency through this interface added for migration, and observe that the guest now was seeing a different TSC frequency.
That's pretty cool. So this is actually having the guest report into effectively the hypervisor. Here's what I am seeing in terms of the passage of time.
Yep.
And then we can check that. Yeah, that's really neat.
Yeah, it's super cool. And it made me feel a lot more confident, obviously, that it was working.
Right, because we were obviously setting up these structures we believe correctly, but it would be nice to just rely on to know that the guest is seeing the correct passage of time. Again, and this is where we would see if we had incorrectly set up the VMCS, or if the hardware itself were broken, we would see it in this test, I assume.
Right, and it's also I had test systems, but they were also the same kind of CPU hardware. So even if the frequency is different, it's a lot harder to assess whether things are incorrect if they're that close in frequency.
Yeah.
But if you change it to 2x, then that should definitely be noticeable.
So did your kind of early experiences where this kind of it did work okay some of the time before you'd done any of this work? Did that kind of change your disposition in terms of testing this? It seeming to work is really not sufficient. We've really got to test the crap out of this to actually know that it's actually correct.
Yeah, I still have other types of tests I want to do. It's just very hard to verify, but I think I did everything I could from a kind of basic testing perspective. I think something that would be cool to do over time is more stress testing, or leaving guests running for a really long time. Definitely moving between more interesting hardware would be cool. It's something that's very easy to see that the math looks right, but then these small variances that can accumulate over time, I think, are harder to reason about, and that's why I'm kind of interested in doing longer running tests or stress tests.
Yeah, totally. And you did this for both. Had to do this for both Intel and AMD, because we obviously want to support for the upstream Lumos work.
So I actually only did it for AMD because I didn't have access to an Intel cluster, but it is written such that it's not going to break on an Intel machine. You can use these interfaces on Intel. The only thing you can't use is the frequency control. That was part that I did not go do.
Got it.
So you could, in theory, migrate between two Intel machines, but they would have to have the same frequency, or we could, change that to be more lax if that's something that would be useful. But it'd probably be better to just do that work.
Okay, so but you've got the work where someone could go do that and kind of plug it in if they cared about I guess this would be someone who's running. Well, I guess it would have to be Propolis. Something else that's doing live migration. Some other, because beehive is just maybe it's worth distinguishing the difference between beehive and Propolis.
Yeah, so beehive is the in-kernel VMM portion that's in upstream Lumos, and Propolis is the user space component. So there's a lot of emulation that happens at both layers. So some devices are done in Propolis. There's some stuff around device interrupts and sort of common shared things you might need between devices that is in beehive. The interface that I added for migration is at the beehive level. So if someone wanted to use a different user space or use Propolis, it's all at the user space boundary. So it's available.
And one of the problems we're trying to solve with Propolis is that I don't know if folks have been into either QEMU. Have you been in the QEMU source, Adam?
No, never.
Oh God, it's really, it's very. C is okay, fine. C has got some some safety problems, but you go into a queue and you're like, holy mackerel. I mean, this is just, and I mean, it in part, it just means that it's pretty easy to actually make QEMU croak by doing things that are out of bounds with respect to a device, for example, which is, on the one hand, not something you would do on actual hardware because, like, the device will, I mean, it's going to have ill effects on actual hardware, which is kind of disincentivizing it, on QEMU, but we really wanted something that was much better. And the Beehive usually had a lot of the same problems. So that's part of the reason why when we started the company, Patrick, Propolis, by the way, is bee glue.
It's important to mention. Yeah.
It is important to mention. I think it's a great name. So that's part of it. And we looked at Firecracker, but Firecracker's fine, but it's definitely doesn't have the same objective that we had around running big VMs that are full-featured VMs, running Windows or running Linux or running BSD, and can run for a long time and can live migrate. And Firecracker was designed for much smaller kind of things.
Earlier, you asked about like the testing pattern of where things kind of worked sometimes, so it's like hard to tell that it's fixed. And I was thinking about how a lot of debugging I did for this was actually not around the TSC at all. It was all for other problems with migration, because that is still something that was leading edge at the time. So a lot of what I was debugging were like serial console issues or like issues with the way we migrated certain devices. And that was all very valuable, but it's kind of like funny to me that most of the debugging I did was for other things, but that's just life at the bleeding edge, I think.
Yeah, it's life at the bleeding edge. So describe that a little bit, because I mean, it's like, it is actually really hard to migrate a bunch of this stuff, and like migrating a serial port or a serial console is actually really hard. And like, why would you bother? Like, why do we even why migrate the serial console? Why is that important?
I mean, as engineers, I think a lot of us love the serial console as an out-of-band mechanism, right? There's a lot that goes into migrating the console. Itself is backed by a couple devices, like the UART emulated device, but then also we have all this control plane upstack work around all of this that kind of provides the actual feature to users to provision instances and use the console, and all of that has its own state that also gets dealt with in migration. So it's actually like a pretty complex stack in the end, but it is very nice how much effort, particularly Lyft, has put into making migration of the console work so well. And it made it a lot easier for me to test this, actually, because I didn't have to set up networking on the guest. I could just hop on the console. It was super simple, and like run whatever test I was going to run, migrate while those were running. Yeah, I mean,
I gotta say, I love our collective emphasis on the serial console. I just feel like it's
incredible.
The serial console.
Yeah.
It really is incredible for like for a machine that has no serial port. I mean, there is no serial port on a Gimlet. We love the serial console for our serial consoles for guests are really valuable, because the other thing is, like, you can then plumb that through into the actual web console. And David Crespo and his team have done such a tight job on that stuff. I just think I for one support our emphasis on the serial console, and because it's really essential if you're actually looking after a VM and trying to understand, in particular, like, why does networking not work? If you don't have a serial console, that is a VM that's lost at sea. So it actually is really, really important that the serial console work all of the time and be really robust. And
it also
that means
enables development, right? Like, for a while, networking wasn't super stable in migration, and it would have been hard for me to run those tests if I didn't have the console. It's really load bearing. I was actually also thinking about how kind of a lot of the ways that we as a team worked on migration, I think are some good patterns, I think, to emulate in terms of engineering over a long period of time. But for a while, we had this like variable in the kernel, basically, that was like, allow writing state to these kind of interfaces that are used for migration. And by default, that was off because we were still, it's still, like I said, bleeding edge work, and we were finding issues and didn't want to break upstream users somehow accidentally use that interface, I guess. That really enabled us to continue merging upstream, like and iterating quickly on all these different pieces of migration that were required. So again, just like looking back on this project, a lot of things I observe are like how much other work enabled development of this, and how like I think we continue to do that as a team, which is pretty cool.
Yeah, definitely. So elaborate that a little bit. So we had this effectively a flag that when you say upstream, you're talking about upstream, Illumos, behind.
Mm-hmm.
Yeah, and so we really wanted to live upstream as much as possible, and upstream as much of our work as possible. Propolis is obviously all open. We've seen the disadvantages of kind of unintentional divergence when you don't really aggressively upstream. So that's been really important for us.
I mean, if I think about us all having to work on a project branch for as long as migration work has been ongoing, it would be unbelievable, the diff. Like, so difficult to manage.
Oh man, yeah, there were, and I mean, Adam, you remember when dtrace, SMF, CFS, Fire Engine were all targeting the same release of the operating system, and it got real rocky. We went in first, right? I'm not just retconning there.
I think that's right, and not by accident, because we were kind of forcing everyone to merge with us. Well,
right.
And other folks had actually preemptively merged because they wanted to use dtrace in their own development.
That was great, actually. The fact that the folks. So I guess we were actually not really suffering with that problem because we were but it is tough when you've got a big body of work that's living downstream. It's really, and Jordan, I think in terms of like finding what are some iterative paths that you can use to get stuff upstream is really important to get to be able to because you also don't want to have this problem where you still have like the last 10% is actually the 90% of the work. You really need to kind of polish bits as you go and get that completely upstream. And that's always a challenge for something that's, I mean, this is a big build and it's kind of a multi-year project.
And it enables new testing too. Anyway.
What do you mean?
Oh, just that like if it's in upstream, we're collectively testing it more if we're using those interfaces. I don't know.
Yeah, and when I also feel that like the other advantage of upstreaming this stuff is it really forces us to kind of explain everything that we've done to kind of the world. And I mean this work that you did had a lot of really great block comments in here explaining. Not, of course, we would have done that. We weren't upstreaming it, but very verbose comments that we obviously all love, and kind of explaining what the problem is and the solution.
Yeah, for sure.
This is great work. Well, Jordan, this is a lot of. I think it's one of these problems. Did you think this problem was going to be like? I mean, surely this is like deceptively complicated. We're just like, how complicated can it be? You're like, oh my god, this actually is pretty. I mean, doesn't this problem fall into that category for you?
I think so. I think the hardest thing for me is like a lot of it is not intuitive. If you're like, I tried to write things down in a very authoritative way, right? But coming into that, I couldn't find a lot of writing about this problem, even though surely other people have done it. Maybe it's proprietary. And so coming up to it for the first time and kind of working through everything from first principles and going off of existing documentation and the manuals or whatever, it was like a lot of things just didn't feel intuitive to me. So writing it all down and block comments was very important. Like before this call, I reviewed my own block comments because it's been a little bit. I'm like, I probably forgot all these details.
Oh, yeah.
And
yeah, you and me both. I was reading my block comment in cyclic.c as of this writing in 1999. And
wow.
It's like, all right, yeah, exactly right. I know. Just don't. Yeah, I know that you were definitely alive in 1999, but like certainly my own children were not. So it's turning into a while ago. But it's very nice to have. Actually, Jordan, I've got to ask you this because you're someone who writes very well and fluidly. When you are looking at an old block comment of yours, do you remember where you were when you wrote the block comment?
Physically?
Yeah. Am I the only one that does this? Am I being weird?
Sometimes.
Am I doing the weird thing right now?
Depends. Yeah.
Are you just saying that for my benefit? Am I being really weird?
I only work in basically 2 locations, so it's pretty easy.
I remember and I don't know, maybe if it's the time I was where I wrote a lot of stuff, but I can remember I wrote so much code and especially comments on Caltrain, Adam.
Right. Yeah, I think
I mean,
actually from that kind of era, I have like stronger memories of like being on a plane to Shanghai or this part of Detrace I wrote when a house 2 doors down caught fire and I couldn't get back to bed. But maybe less of it now. It's become more like homogenous.
we're not going to just drive past that one, are we? Are we just going to pretend that
You
that
actually
didn't
remember
happen?
that fire? It was like 2 blocks from you too. It's a huge
Oh, I
fire
definitely
in
remember that
Sherwood
fire.
Hill. Yeah.
But my first thought on that fire was not like time to write some code.
I was just like
Like you
too
were writing
agitated.
code during that fire?
No, not during the fire. I think like after it was in hand, it was like 4 a.m, and I was like, okay, now what?
Okay, I definitely
Yeah,
so just for context, you and I lived only that fire was like right between us.
that's right. That's right.
And that is still like the biggest house fire I feel I've ever seen. I woke up to ash going through our apartment.
Yeah, second
And I
closest for
could
me now. The closest was one where I came back home and I was like, okay, let's make sure we know where the dog's leashes are and everyone's shoes are, because I was only a few doors down from us. But
that one was kitty corner across the street and one house down. And it was
yeah, there you go.
that house was engulfed in flames. I mean, it
Yeah.
was, and the houses all abut one another in San Francisco. And man, people can talk about the decay of San Francisco all they want. Man, that city knows what to do when it's burning to the ground. I mean, there is something deep in the DNA of that city. Is like, here's what we do, and I mean, I actually just still remember it really viscerally because this thing is like we had like ash coming through the apartment. I could hear the fire. I could hear it crackling. I could feel the heat and watching, and it was a 3 or 4 alarm fire. So you had they brought the cavalry to that thing, and watching the firefighters, because I had never been so close to something where it always felt like fear, and watching the firefighters put on their gear to jump into the building. I'm like, man, that's crazy. I mean, and I've always kind of in whatever domain you are, the courage to kind of jump into the blaze is, I mean, that's the real hallmark of the professional, is like jumping into the blaze and not being afraid of it and not being afraid. For us in software, it's Jordan, it's like you not being able to, not being afraid of, jumping into the problem or starting the prototype or what have you. I feel it's like less bodily harm involved in general.
That's how you feel?
I just can't believe that after that fire, you're like, okay, well, time to write some code. I'm like,
No,
time
it
to stop
inspired me.
thinking from a fight or
Inspired me
flight
to jump
reaction.
into the blaze. I was like, these guys, and look at me, just napping in my bed,
Oh, well played.
getting
Time
soft.
to jump into dtrace stubber.s. Gonna put on my oxygen tank and go into dtrace fish.
Yeah, there you go.
Well, Jordan, this has been, I still don't know exactly how we got to house fires from this, but metaphorical or otherwise. But this has been great, and it's really great work. It's exciting to see. And I mean, you've been doing a bunch of work on the Propolis side. So this is you've got more work in this department coming up, presumably.
Yeah, I've been jumping around the stack a little bit lately, but definitely got lots more on my mind about Propolis. So.
Did I mispronounce Cavalry? Cavalry. Oh no, we're doing this again. I'm sorry. I'm in the chat. I didn't even thought that when I was pronouncing it. How do you pronounce it, Adam? Cavalry? Cavalry.
I just avoid it. I don't know.
I definitely
one of those ones.
Said it wrong.
Our Marine in chat says cavalry.
Cavalry. Did I pronounce it, Dan? Did I pronounce it correctly or incorrectly when I initially pronounced it? That's actually all I need to know. It's just that high order bit. Why am I even asking this question? I don't want to know. I do pronounce. Oh yeah, exactly. There you go, Dan. Well played. And there's the block comment, Adam. From 1999. The go days of 1999. I remember where I was when I wrote that thing. I remember I was at a cafe in Palo Alto. All right. Well, this has been a lot of fun. And Jordan, again, great going on this work, and a lot of fun other work besides, in terms of not just the simulator, but all the testing you did and the stereo console and the works. It's been a good little whirlwind tour of what we've done for VM migration.
Oh, thank you.
You bet. And then, Adam, next week, I think we are going to have our colleague, Greg Colombo, to talk about TLA Plus and formal methods and some of the work that he's done in that department.
Another hypervisor special.
Another
Yeah.
hypervisor special. It's hypervisor month here on Oxide and Friends.
All right, I'm into it.
Exactly. This is like Shark Week for Oxide and Friends. We do hypervisor month. And is Tom Lyon here? Tom, I hope that's you in the chat. I got to tell you, I've been listening to a lot of Adam, we were listening to a lot of the back catalog in preparation for when we did our On the Metal on Oxide and Friends. I was
the crossover, yeah.
We got to get Tom in here. So Tom, I'm glad you're here. And we've got I definitely missed you and loved your line about the funeral for Opteron being a goldfish funeral. Is still one of my all-time favorite lines. So on that note, we will see. Hypervisor month continues next week. Join us.
Love it.
All right. See you next week, everybody. Take care.